Welcome to Linear Algebra. We're going to just jump right in with these recorded lectures and start with the first couple of sections, 1.1 and 1.2. Um, uh, some of these lectures will have a couple of sections together all at once. Some will have just a single section. Today we're going to talk about two things at once which really fit together pretty nicely. We're going to look at systems of equations, row reduction algorithm, pivots, free variables, and general solutions to systems of equations. Now, these are all things that, at least at Oakton, we talk about in our college algebra course. It may have been some time since you've thought about those and seen those, so you may have to go back and review some of those things, but I'm going to give you a short overview of what was going on with those. Turning a system of equations into a matrix, applying an algorithm to read off a solution in an easy way. So that's our goal for today, and we will jump right into that. Before that, here's a simple system of equations, a system of linear equations that we might ask to solve. X1 minus x2. So we have two equations and two unknowns, and we need to solve for x1 and x2. Now, in this simple case, there's an easier way to do it than what we're about to look at. But when we move on to systems of 3 equations and 3 unknowns, or 5 equations and 5 unknowns, then the matrix version becomes actually the most efficient method of solving this equation. So you might suggest, well, solve for one variable, solve for x1, say, in this equation 2, substitute it in here, and then we can reduce our variables. And that's true. But I want to remind you of the other way that you would have learned in college algebra to solve this via a matrix. So I can think about this as a matrix, 2, 1, so we've got our coefficient matrix. We call this our augmented matrix for the system of equations, where we have our coefficients and our constants on the right. We're going to often see these dotted lines in between here to indicate that this really is a system of equations, and these are the constants, but sometimes a dotted line won't be there, and we still have to remember or recognize what the situation that we started with, how that leads to a matrix. And in this situation, this is just our augmented matrix corresponding to this system of equations. Now remember, one thing that we could do here is we could actually just add these two equations together, and that would remove x2 because I have plus x2 and a minus x2. But again, from our college algebra course, let's remember our actual procedure that will row reduce the matrix and get it into a form that we can read an answer off of. Okay, so what I'm going to do is I'm going to pivot around this 2. That is, I'm going to make this into a 1. We'll do that in a minute, and zeros above and below it. So let's do that first. So what I'm going to do is I'm going to take row 1. I want to turn this into a 1. So that in order to do that, I'm going to take the entire first row and divide it by 2. So I'm going to take row 1 is going to become 1/2 of row 1. So that this becomes 1, 1/2, 1/2, and nothing else has changed. So we took this 2 and we turned it into a 1. If you don't remember why that's important, well, we'll see in just a few minutes why that's actually very helpful. Now I can take this and turn it into a 0. Every time I've got a pivot position, we're going to turn the pivot position into a 1. And so our first pivot position is always our upper left corner. Once we get a 1, we'll turn everything below it and above it, depending on where we are, into a 0. And I'm going to do that by taking row 1, multiply by -1, and add it to row 2. So row 2 is going to become negative row 1 plus row 2. Let's put that down here. And let's see why that's helpful. I haven't changed row 1, so that stays as 1, 1/2, 1/2. But row 2 is now negative row 1 plus row 2. So negative row 1 plus row 2, that's negative 1 plus 1 makes a 0. And that's what I wanted. I wanted a 0 here. Negative row 1 plus row 2, so that's negative 1/2 plus negative 1/2 is negative 3/2. Negative row 1 plus row 2, negative 1/2 plus 2 is positive 3/2. All right, so far so good. We started with our upper left-hand corner, turned it into a 1, and then we made zeros below it. There was only one position below it, and so this became a 0. We go to our next pivot position, which we get by moving down from our previous pivot position and across, if we can. So we went down and over. We're trying to make pivots going down at an angle. Remember, again, this is, and then we're going to turn this into a 1. How do we do that? Well, row 2, I'm just going to multiply by negative 2/3. If I multiply through by negative 2/3, that position becomes a 1. So negative 2/3 row 2. And that makes this a pretty simple row. 0, 1, negative 1. And I haven't changed row 1. So my next pivot position has become a 1. And we need to clear out everything above and below it. So we make zeros above and below. There's nothing below, but there is something above. We can turn this into a 0 by multiplying row 2 by negative 1/2 and adding it. Because if I want to get rid of 1/2, I need to turn this into a negative 1/2. So row 1 becomes negative 1/2 row 2 plus row 1. Negative 1/2 row 2 is 0, plus row 1 is 1. Once we have a pivot position at a 1, it will never change. Negative 1/2 times 1 plus 1/2 makes 0. We wanted that to be 0. Negative 1/2 makes 1/2, add it to 1/2, and I get 1. And I haven't changed row 2. 0, 1, minus 1. Remember, the whole idea with this row reduction process is that we started with a system of equations, we turn it into a matrix, we apply this process by finding pivot positions, making zeros above and below, and then return this to a system of equations, and whatever solution this has is the same solution as the initial. So let's return that matrix to a system of equations. If we look at this final matrix, why is it final? Well, there are no more pivot positions. We found a pivot, we made a 0, we went to the next pivot by going diagonally down, made zeros above and below. There's no more pivot because I can't go down anymore in this particular matrix. But if I return this to a system of equations, it becomes 1 x1 plus 0 x2 is 1, and 0 x1 plus 1 x2 is negative 1, which is the same thing as saying x1 is 1 and x2 is minus 1. And if we look at our original system of equations, I plug 1 in for x1 and minus 1 in for x2, I get 2 minus 1, that's 1, good. And 1 minus negative 1, which is plus 1, makes 2. So this actually is the solution to the system. So the whole point, the whole process of making these 1s and 0s means that I can return it to a system of equations and really essentially just read off the solution. The solution here is x1 is 1, x2 is negative 1. We're thinking about this as the x1 column, this is the x2 column, and this is the constants column. All right, so let's Let's look at another one that's a bit more complicated. Suppose that my system looks like this. Here's my system of equations. Let's turn it into a matrix. Remember that we need to include zeros whenever necessary. This coefficient, 1, -2, 1, 0. 1, -2, 1, 0. We'll put our dashed lines to indicate that this is the variable side, this is the constant side. 1, 0, because there's no x2's, -1, 1. There's no x1, so 0, 1, 2, 2. And so this is our matrix. And now we need to row reduce it by finding pivot positions and making zeros above and below them. Our first pivot position will always be the upper left-hand corner. Here it is. It's already a 1, so that's good. So we don't need to do anything with that. But we do need to make zeros below it. I already have a 0 here. That's fine. But I need to make this one into a 0. And I do that by I use my pivot, and I use the row that I'm looking to change. And in this case, I'm just going to say negative. So I'm going to make row 2 become negative row 1 plus row 2. Because if I take negative row 1, I get negative 1 plus row 2, which is 1, and that turns that into a 0. Row 1 hasn't changed. If I apply this, negative row 1 plus row 2, I get 0. 2 plus 0 is 2. Negative 1 plus negative 1 is negative 2. 0 plus 1 is 1. I'm not going to change row 3 because I already have a 0. We look up for our next pivot position by going down and across. So 2 is our next pivot position. We look to change that into a 1. And we have a couple of options at this point. Remember, one thing that we can actually do is switch these 2 rows. I could just switch these 2 rows. Switching 2 rows is fine. If I did that, then I'd get a 1 here, and I wouldn't affect the fact that I have a pivot here and zeros below it. Or we could just divide by 2. Either one is fine. In the end, it'll cost you the same amount of work. Let's just divide by 2 right now. So let's just take row 2 and replace it by 1/2 row 2. And if we do that, I haven't changed anything here. 1 minus 2, 1, 0. 0, 1, minus 1, 1/2. 0, 1, 2, 2. Now what? Well, now I have a 1 in my next pivot position. I need to get zeros above and below. So we're going to do that by, now that I have a 1, it makes my life pretty easy. If I want to get rid of a -2, I just multiply by 2 and then add. So row 1 will become 2 row 2 plus row 1. So that I have 2 plus -2, which makes 0. If I do that, 2 plus row 1 is 1. Once I have a 1 in a pivot position, it will not change. 0. 2 row 2 makes -2 plus row 1 makes -2 plus 1, which is -1. 2 plus 0 is 2. Row 2 isn't going to change because I've got my pivot position at a 1. Row 3, I'm also going to change because I'd like to get zeros above and below my pivot positions. So I can do two things in one step here. Let's turn row 3 into, I just need to get this to be a 0, so I'm going to take a negative row 2 plus row 1. Negative row 2 plus row 1. In which case this becomes a 0, the 0, 3, and 3/2. And we're making our way through. We've got a pivot, zeros below, a pivot, zeros above and below. We move to our next pivot right here, and we're going to get rid of this or turn this into a 1 just by dividing by 3. So row 3 will become 1/3 row 3. And that's what we find. Now that we've made our final pivot position into a 1, we need to get zeros above and below it, in this case just above. If we move back through, the next step here, I need to get rid of this negative 1. I'm just going to do that by taking row 1 and row 3 and adding them up, because 1 and minus 1 makes 0. So row 1 will become row 1 plus row 3. Row 3 isn't going to change, but row 2, since that's also a minus 1, I'm just going to add it with row 3 as well. Let's do those both at once. Row 2 will become row 2 plus row 3. Notice we're always using, if I'm changing row 1, I'm going to use row 1 plus the pivot row. If I'm changing row 2, I'm going to use row 2 plus the pivot row, or minus the pivot row, depending on where we are. All right, so let's see what we get. If I change row 1 and row 2, row 1 becomes row 1 plus row 3. Row 1 plus row 3 is 1, 0, 0, 5/2. 2 plus 1/2 is 5/2. Row 2 plus row 3 is 0, 1, 0, 1. Row 3 doesn't change. 0, 0, 1, 1/2. Which means at this point, I can actually read off my solution to my initial system of equations. Because remember, this is the x1 column, x2 column, x3 column, constants column. So my solution is x1 is 5/2, x2 is 1, x1 is 5/2, x2 is 1, x3 is 1/2. And if you go back and check this in the initial system that we have written down, you'll find that it works in all 3 of the equations. All right, now, it doesn't always work quite as simply as that. A couple of other things can happen. Suppose that my system of equations has an augmented matrix that looks like the following. Let's row reduce this, see what we get. We'll see that something a little bit different happens. So if I row reduce this, I've already got a pivot, so I'm not going to change row 1. But I am going to get zeros below my pivot. And if I do that, then I'm going to take row 1 and row 2, negative row 1, and add it to row 2 to make this into a 0. And I get 0, negative plus this is 2, negative plus this is negative 2 plus 1 is negative 1, negative, so 1 plus 3 is 4. Negative, how do I get this into a 0? Negative 3 times row 1, add it to row 3. So that's 0, Negative 3 and add makes 4. Negative 3 and add makes negative 2. Negative 3 and add makes 8. We look for our next pivot, down and across. Here's our next pivot. So we turn that into a 1. 1, 0, 2, minus 1, 0. By dividing by 2, 1, minus 1/2, 2. And I won't change this. 0, 4, minus 2, 8. Pivot, we need zeros above and below. We've got a 0. We need this to be a 0. So negative 4 and add. Negative 4 and add makes 0. 0. We multiply this by negative 4, then I get 4 which is 2. And then I add it to negative 2 and I get 0. Negative 4 and add makes negative 8 and 8, which is 0. So that's our next matrix. Now, this is different, right? Because here's our pivot. If I wanted to look for the next pivot, I would go down and across. But I can't make that into a 1. There's no way to make that into a 1. Because if this were 6, how would we make it into a 1? I'd divide by 6. But I can't take 0 and divide by 0. So this is the best that we can do. And sometimes we'll end up with a matrix, which is not as nice as the one that we'd like it to be. But it's the best that we can do. And so let's see what happens if we return this to a system of equations and understand how we can write down our solution. So if I return this to a system of equations, it becomes 1x1 plus 2x3 is negative 1. x2 minus 1/2 x3 is 2. This last line says 0 is 0. 0x1 plus 0x2 plus 0x3 is 0. And that's okay. 0 does equal 0, so there's no problem there. All right, but I'm going to do one other thing here before I say that we're done writing the solution. What does this mean? All right, so this means that I'm going to think about x3 as being allowed to be anything that I want it to be. We're going to say that x3 is free. x3 is free. It's free to be anything I want it to be. And no matter what I choose x3 to be, I can figure out then what x1 is and what x2 is. I'm going to put my free variable over on the right and say that x1 is negative 2x3 minus 1. x2 is 1/2 x3 plus 2, and x3 is free. And this is my solution to the system of equations. So you can choose any value you want for x3. Once you choose that value, if you plug it in here, it gets you x1. If you plug it in here, it gets you x2. And that'll get you a value for x3, whatever you chose, and then x1 and x2. You plug those things back into the original system of equations and they'll work, no matter what you started with for x3. And in this case, the system has an infinite number of solutions. Because I could choose x3 to be anything I want. 10 or 2.7 or 136. Or anything I want for x3, that'll force x1 and x2 to be something, but I'll have a solution to the initial system of equations. So when we have a free variable, we have an infinite number of solutions. Which variables end up being free? the variables that do not have a pivot. Pivot for x in the x1 column, pivot in the x2 column, no pivot here, and so that's the one that's free. All right, now, still a few other things might happen. Let's look at those as well. Okay, so let's look at another example. Suppose that I had a system of equations. I started with my matrix. I applied this algorithm, our row reduction algorithm, and suppose that this is what I get. Okay, so notice that this is actually reduced as much as possible. Pivot, zeros below, pivot, zeros above and below. Next pivot is over here, down and across until I get something that I can actually work with. And I turned it into a 1 and then zeros above and below. So this is actually reduced as much as possible. What does this system look like if I turn it back into equations? x1, x3 is 0, x2 minus x3 is 0. This last equation is 0 x1 plus 0 x2 plus 0 x3 is 1. And so that equation says 0 is 0. A 0 is 1. But that doesn't make any sense because 0 does not equal 1. And so if I have something that looks like this, there are no solutions because this is a meaningless equation. It doesn't make any sense. And we say that the system is inconsistent. The system is inconsistent. A consistent system is one for which I have a solution, or maybe more. We saw one a little bit ago, which had an infinite number of solutions. The first examples that we looked at had a single solution, but it's also possible to have an inconsistent system, one which has no solutions at all. Okay, so here's one more that just is about as complicated as it could get. Suppose that I had 4 variables, x1, x2, x3, x4, and then we have our constants. Suppose that I had a system of equations and I applied our row reduction algorithm, and this is what it looks like. So this is what we get. And notice that again, it is actually as reduced as possible. Pivot, zeros below, next pivot, down and across is right here. Zeros above and below, next pivot, nowhere else. There are no other pivots. So in this case, notice that I have a pivot here and here. So these are my free variables, the variables that do not correspond to the pivot positions. So x2 is free and x4 is free. But we're still going to return this to a system of equations, and if I do that, the first equation becomes x1 minus x2 plus 3x4 is 1. The second equation becomes x3 plus 2x4 is 1. And the third equation is 0 equals 0, which is okay. So what I'm going to do in this situation is similar to what we did in the last case where we had free variables. I'm going to put all of the free variables on the right. There will only ever be, at most, one variable that's not free in any particular equation. Because when we have a pivot, I can only have one pivot in any particular row, because the next pivot comes down to the next row. And so there's only going to be one variable that's not free. I'm going to move everything else to the right. And if I do that, then I get x2 plus 3x4 plus 1. That's because x1 is not free. x3 also has a pivot. So I solve for x3. These are always going to be the leftmost variables. Everything else will move to the right. I see negative 2x4 plus 1. And x2 is free. x4 is free. And this is the solution to the system of equations. Okay. So let's summarize what we've learned. We talked about the row reduction algorithm. You should be able to apply that to any matrix. We've talked about how you find pivots in a particular matrix in your row reduction algorithm. We've talked about the words inconsistent and consistent. Remember, inconsistent means no solution. Consistent means a solution or more. And we've talked about writing the general solution by putting all of the free variables on the right. And that's section 1.1. There's a lot of stuff in there. Some of it you should have seen some of this in the college algebra course in the past. You may have to go back and look at it and think about it again. But at this point, you should be in a good position to look at the homework and online quiz for section 1.1. Check it out, and see you next time. Welcome back. Today we're going to think about section 1.3, which has a couple of basic topics: vectors, linear independence, and span. If you are in a Calc 3 class or have already taken a Calc 3 class, vectors in particular should be somewhat familiar to you. We're going to think about those in a bit more detail later, but we'll start with the basics today. So a vector for us is really going to just be a list of numbers. A vector in Rn. So this is a funny shaped R. It's an R with an extra bar over it, and it's really a part of our definition. What I mean by this n is it's going to have, n means how many numbers are in my vector. So let me continue with the definition. We'll talk about it for more. A vector in Rn is an ordered list of n numbers, n real numbers. I'm going to write it like this. Right, so here's a vector. It's an ordered list, and we're going to write them vertically. So 0, minus 1, 2. This is a vector in R3. N tells me how many numbers are in my vector. So there's a vector in R3. 0, minus 1, 2. We write them with a letter, usually V or sometimes U or W, or you're often going to use letters at the end of the alphabet to talk about vectors, to indicate vectors. When I write it on the board, we'll see this little arrow above it. In a written textbook, vectors are written in bold. So on a homework or a quiz or on a written piece of paper on your exams, the vectors will be in bold. In the textbook, they're in bold. When I write them on the board, I'm going to write them with this arrow above it to indicate that it's a vector. So this is a vector in R3. Here's a vector in R2. not allowed to be decimals. Call that U in R2. So it's really just a list of numbers. That's all it is. Nothing special. But we can add and subtract vectors just like we can real numbers. And again, nothing tricky here. If I want to add two vectors, these are vectors in R2, two-dimensional vectors, two numbers. I'm just going to add just the way you would hope. I'm just going to add straight across. Subtracting is the same way. So if I subtract, I just subtract straight across. When I say scaling, what I mean is something like this. I can take a vector and I can scale it. I can multiply it by a number. And when I mean scale, I'm just going to take this number and multiply it by both of the pieces. So I've made both of the components of the vector 6 times as large as they used to be. All right, and so we're going to see that this is going to be useful for us for organizing our notation, and when we talk about matrices, we can do something else with vectors. We can take a matrix times a vector in certain cases. Not always, but if dimensions match up in the correct way. And so I'm going to talk about a couple of ways of how we can do that, and we'll see then how the dimensions will work. All right, so here's what we're going to do. Suppose that I had a matrix that looks like this. Now, I'm not thinking about this as a matrix that corresponds necessarily to a system of equations. All right, this is just a matrix, just entries in different positions. So this is a row 2, 3 columns. So this is a 2 by 3 matrix, row by column. 2 rows, 3 columns. I'm going to be allowed to multiply that by a vector that has 3 entries. This 3 here has to match this 3 here. So this is in R3. This is what we'll call a 3 vector because it's a vector in R3. And we're going to think about 2 ways of talking about how we can multiply these things together. The first way is the following. I'm going to take this, so this has 3 columns, and this has 3 entries. And in order to multiply a matrix times a vector, that has to match. If I have 6 columns, I need to have 6 entries. I'm going to take each of these entries, and I'm going to match it up to one of the columns. So this -1 is going to get matched up to 1, 0. So when I multiply matrix times a vector, this -1, that's the first entry in the vector, it gets matched to the first column. And I'm going to scale the appropriate column by the appropriate entry in the vector. So -1 gets matched to the first column, 2 gets matched to the second column, and then I'm going to add 2 times 2 minus 1, and then 1 times 1, 2. And now we just see what we get. And so remember, when we scale, everything gets scaled. And when we add, we just add the way we would like to add, straight across. So this is -1 plus 4 plus 1. And this is 0 plus negative 2 plus 2. Which is 4, 0. So notice a couple of things have happened here. If I take this matrix, multiply by this vector, the 3 columns matches the 3 entries in the vector, but what do I end up getting back? I end up getting back a vector in R2, a 2 vector. Why? Because I'm taking the columns here and adding them up with certain scaling factors. The scaling factors that correspond to the vector over here. But in the end, I get a 2 vector back because my columns had 2 entries in each column. And then I'm taking this column plus this column plus this column scaled in different ways. All right. Now, that's fine. That's how we actually want, that's one way that we want to think about matrix times a vector. Usually when we actually physically write down a matrix times a vector and calculate it, we're not going to go through this middle step. Notice what did we do to get -1 plus 4 plus 1? I got -1 times 1 is -1 times 1 is -1. So if I take this and this, and then if I take 2 and 2, I get 4. And then if I take 1 and 1, I get 1. So this -1, 4, and 1 comes from taking this piece right here. Think about physically picking it up, flipping it over, and matching it to there. Right, so I get the 1, -1, 4, and 1. And that's what makes that top entry. So that's row 1 and column 1, if you want to think about it like that. Gets me the row 1, column 1 entry. Row 2, so 0, -2, and 1. That's the 0, -2, sorry, I said 0, -1, 2, and 2. 0, -2, and 2. That's what this entry comes from. And so that's how we're actually going to multiply matrices in the end. We want to think about this as columns scaled differently, and we'll see why when that becomes useful. But when we actually just are trying to calculate matrix times a vector, we'll think about it in that second way. Let's just look at another example of that. Okay, first, suppose this is my matrix. What kind of vector can I multiply it by? You should think about that for a second. All right, so how many entries does this vector have to have? Hopefully you've decided that the answer is 2. It has to have 2 entries because the number of entries has to match the number of columns. So there are 2 ways you can think about it. I'm really going to literally think about taking this 1, 6, lifting it up, flipping it over, and matching it to there. So there has to be 2 entries. This has got to have 2 entries. So this is, let's say that this is -1, 4. So that's got to have 2 entries. When we're done, what are we going to get back? When we're all done, we better get back a vector that's in R3. A 3 vector because we're taking these columns and adding them up with the different scalings. So if we take 2 vectors in R3 and add them up, I still get a vector in R3. So in the end, we're going to get back something that's in R3, a vector with 3 entries. What is that vector actually going to be? Well, let's remember. When we multiply matrix times a vector, I'm just going to take, again, thinking about this 1, 6, matching it to -1, 4. 1 times -1, that's -1. And then 6 times 4 is 24. And that's the first, and add. That's the first entry. So you get to the second entry, 0 times -1, which is 0. And then 2 times 4, which is 8. And then -2 plus 4. And so my answer is 23, 8, 2. Okay. So how does this relate to what we talked about in the last sections? Okay. Notice that first of all, this makes sense because this vector has 3 entries. I don't know what they are yet, x1, x2, and x3. It has 3 entries, which matches the 3 columns here, so I actually can multiply. And when I am done, I'm going to get back another vector that's in R3 because I'm taking the columns and adding them up with the corresponding scaling, which will be another vector in R3. So this will equal some other vector in R3. And I can say, what is x1, x2, and x3 that will solve this equation? Okay, so if I call this the vector, the matrix A, this the vector x is a vector, and this the vector B, what I'm saying is solve AX equals B for x. And that's a question that we can ask. Figure out what x1, x2, and x3 are that will make this work, if there are any. Now, that's fine. How would we actually go about doing that? Notice that if I apply my thinking about matrix times a vector as columns scaled by the corresponding entries, I'd get the following. Well, actually, let's think about it in the other way. Let's think about it. How do we actually multiply a matrix times a vector? 1x1, 2x2, 1x3. x1 plus 2x2 plus x3. 1 times x1, 2x2, 1 times x3. The next one, 0x1, 3x2, and then minus x3. And the last one, x1, 4x2, and then 2x3. So that's this left-hand side. That has to equal 0 to 4. But when does a vector, this is a vector, right? Because this is just some number. When I add everything up, I still don't know what x1, x2, and x3 are, but whatever they are, they're numbers. And I add them up, I'm going to get a number that's got to equal 0, equals 2, and equals 4. So in the end, this becomes x1 plus 2x2 plus x3 is 0. 3x2 minus x3 is 2. And x1 plus 4x2 plus 2x3 equals 4, which is a system of equations. Which is something that we could have answered using the techniques from the last section. How would I actually answer that question? Well, I'd build an augmented matrix. 1, 2, 1, 0, 3, minus 1, 0 here, 2, 1, 4, 2, 4. But notice that we did a lot of work to get back to what we started with, because this was the matrix A that we started with, and this was the vector B. So solving AX equals B comes down to solving this system of equations, which comes down to making an augmented matrix A and B. All right, so we'll look at some more examples of that and actually solve them as well. All right, so let's apply this new way of thinking about matrix multiplication by a vector to answer a question. So let's solve AX equals B for X if A is the matrix 2, 1, minus 1, 0, 1, 0, minus 2, 0, 1, and B is the vector 3, 2, minus 1. All right, so remember that this actually corresponds to a system of equations, but the way to solve that system of equations is to create the augmented matrix out of A with constant column given by the matrix B, and then reducing it. All right. So you'll also find a short tutorial on my math labs for how to use our TI-83 or 84 calculators to come up with the reduced row echelon form of any matrix. So at this point, I suggest that you pause this video if you haven't yet looked at that tutorial, and view the tutorial, and then come back to this video and continue watching here. I'm just going to use my calculator to enter this matrix and calculate the reduced row echelon form of the matrix. Let's enter our matrix into the calculator. So again, I'll say the words. Hopefully you follow along. So second matrix, the second X inverse. You get into the matrix menu, and I'll edit the matrix A, which is now 3 by 4. 3 rows, 4 columns, and we'll just enter our matrix. 2, 1, minus 1, 3, 0, 1, 0, 2, minus 2, 0, 1, minus 1. Enter our matrix, exit out, so second quit, back into the matrix menu, math, over to the math, and go down to command B, reduced row echelon form of the matrix A. And what we find when we do that is the following matrix. 0, 1, 0, minus 1 half, 1 half, 0, 1, 0, 2, 0, 0, 0, 0. So that's what we find as the reduced row echelon form of this matrix. So what does this mean? Remember that this is an augmented matrix corresponding to a system of equations. So if we return that to a system of equations, we see that the top line reads x1 minus 1 half x3 is 1 half. x2 is 2. 0x1 plus x2 plus 0x3 is 2. And x3 has no pivot in it. There's no pivot in column 3, so x3 is free. Which means the general solution to this system of equations would be x1 is 1 half x3 plus 1 half, x2 is 2, and x3 is free. Now, that doesn't, we have to go 1 or 2 more steps for this type of equation because we're asked to actually solve for x, which is a vector, and we haven't yet written down a vector. So let's keep this in mind. Save that bottom stuff for now and see how we can actually write the solution. All right, remember that x3 is free means that x3 is allowed to be anything I want it to be. So I'm going to pick a variable, a value for x3, and just fix it there. So let's say that x3, let's call x3 the letter t. And we can pick t to be anything we want it to be. So if x3 is t, then x1 is 1 half t plus 1 half, and x2 is 2. And all that I did was pick a letter, a variable for x3, which was free, so I'm allowing it to be anything I want it to be. And now I'm going to write this as a vector. And so what's my vector? The vector is, x is the vector, x1, x2, x3. So the vector x is 1 half t plus 1 half 2 t, which I can rewrite like this. If I factor a t out, I get 1 half I get 0 t's here, and I get 1 t here. And if I look at the constant terms, I get 1/2, 2, 0. And so this is the solution to my equation in vector form. We call this parametric vector form of the solution. But notice, there's really nothing too different about what we've done here. We started with this equation, said solve for the vector x, but that really comes down to solving a system of equations rather than writing it in the general form from before. Since our question was a question about vectors, we write our answer as a vector. The fact that we had a free variable means that we're going to have a variable in our answer. If I choose anything for t and plug it in here, then the x value that we get back will solve that equation. So as before, we say that this system is consistent because it has a solution. All right, let's look at another one. Let's solve ax equals b for x if A is this matrix and B is this matrix. So we're going to just do exactly the same thing. We're going to create the matrix out of A and B. We're going to enter it into our calculator, and we're going to reduce row echelon form. So if we reduce row echelon form, this matrix, what we find is the following. This is the reduced row echelon form of this matrix. Again, all I did was use my calculator for a shortcut of that whole reducing algorithm that we talked about previously. What does this mean? Well, we can see at this point that this equation is still consistent because it has at least one solution, but we can see that it has exactly one solution. There are no free variables. Every column has a pivot, except for the constant columns at the end. And I can see that the answer is exactly this vector. x1 is this, x2 is 2/7, x3 is 1/7, which means that I can write that x is x1, x2, x3, which is 1/7, 2/7, 1/7. And that is the unique solution to this initial system of equations. Now, keep in mind that we can still get an inconsistent system out of this. Right? So when would our system be inconsistent? Ax equals b has no solutions if we would start with A and B, and then we would reduce, and we get something that looks like this. Remember, if the final row reads 0, 0, 0, and then any other constant. Maybe there's even more zeros. But if the final row yields 0 equals 1, that doesn't make any sense, so it's inconsistent. And that certainly can happen in this situation as well. All right. Now, we have a couple more things that we need to think about from section 1.3. And the first is linear independence. So here's the idea. I'm going to write down a definition which looks kind of complicated, and then we're going to see that really it comes down to row reducing a matrix. As I said at the beginning, almost everything that we do in this class, almost every question that we ask has a matrix that we have to row reduce and then see where pivots are or see where the last row looks like or do something and interpret the matrix that we get after we row reduce. But so here's the idea. So we say that vectors are linearly independent. And we want to think about, so linearly independent in our head means that they point in different directions. Later we're going to think about a geometric way of understanding vectors in terms of pictured arrows. But for now, our definition is a little bit more technical. And we say that a set of vectors x1, x2, all the way through something, xn, is linearly independent if the only way for c1 x1 plus c2 x2 plus cn xn equals 0. Notice what I've done. I've got a set of vectors. We're going to look at examples of these. But I've got a set of vectors. I'm scaling each vector by some constant out front. So each vector is scaled by some different amount. Then I'm adding them all up and I'm saying, can I get 0 back? And we're going to say that these vectors are linearly independent. If the only way to do that is with all of those constants to be 0 themselves. Because notice that if I put C1 is 0, C2 is 0, C3, all the way to Cn equals 0, that certainly works. We're saying that vectors are linearly independent if there's no other way to do that. So definition, and it feels technical. We're going to come up with other ways of thinking about that and a way of understanding how we can actually figure out if vectors are linearly independent. Okay, so notice. So R, how about these two vectors? 1, 2, and 2, 4. Linearly independent. The answer is no, and we can see that by noticing that 1, 2 multiplied by 2 plus 2, 4 multiplied by -1 is 0. But I can scale this, scale 1, 2 by 2, and I get 2, 4. And so if I subtract those vectors, then I end up getting 0 back. This vector is just a scaled version of this vector. So in the future, we'll see that that means that they point in the same direction. They're just scaled versions of each other. So they are not linearly independent. They are on the same line. And so what that means is because I can do this, because I can scale them and add them up and get 0 back, 0 as a vector, then the answer is no. They are not linearly independent. Now it can be more complicated than that. I can have 3 vectors as well and still see the same thing. So R, how about these vectors? The answer to this is still no, because I forced it to be. Because notice that if I take 2 times the first vector, and then I add it to the second vector, that's 2 plus 0, which is 2. 4 plus 2 is 6. Minus 2 plus 1 is negative 1. I end up getting that last vector back. So in other words, I can create the last vector. Doesn't have to be the last. I can create one of the vectors by using scaled versions of the others. And if I can do that, so this is true, right? So I have 2, a scale factor of 2, scale factor of 1. Put them together and I can get this third vector out. All right, well, if this fact is true, then think about taking this vector and subtracting it over to the left. If I subtract it over to the left, then I get this equation here, which means I have the 3 vectors scaled up, and I get 0 back. So if I can create any one of the vectors by just using scaled versions of the others, then they are not linearly independent. No, we're going to call them, if it's not linearly independent, we're going to call them linearly dependent. Because one of them depends on these 2. And I can take this vector and say that it only depends on this and this. I can use these 2 scale versions of them to create this. So they are linearly dependent. Now that's all fine. But how do we actually determine, if I just give you a set of vectors, if you can't just see the answer, we want to figure out how we can come up with the answer. What's the process that we could use? So how do you decide? Well, let's look at an example. Are these vectors linearly dependent or independent? That's our question. Alright, so remember, what are we actually trying to do? Yeah, I'm trying to say, can I add up scaled versions of these and make 0? Because if I can say, if I can find a C1 to put here, a C2 to put here, a C3 to put here and get 0 back, that means I can put 1 on the other side and say that this one is written as a combination of the others, which would mean that they are linearly dependent. So what I'm really looking for here is C1 times minus 1, or times 1 minus 1, 0, plus C2 times 2, 1, 2, plus C3 times minus 1, 2, 0, and I'm trying to get 0 back. That's what we're looking for. Solve this for C1, C2, C3. Can I do that? That's our question. But notice that if we think about vectors and matrix multiplication by vectors, that I can rewrite this equation as the matrix 1, minus 1, 0, 2, 1, 2, minus 1, 2, 0, multiplied by the vector C1, C2, C3 equals the vector 0, 0, 0, the 0 vector. Why does that work? Remember that a matrix times a vector is given by the columns of the matrix scaled by the entries of the vector. So C1 corresponds to column 1, that's what we got. C2 corresponds to column 2, again right here. C3 corresponds to column 3, right here. But now we know how to answer this question. This is just like AX equals B, which we just talked about a few minutes ago. So how do we get that? And solve for X, or C1, C2, C3. Well, we make the matrix 1, minus 1, 0, 2, 1, 2, minus 1, 2, 0, 0, 0, 0, and we reduce it, and we see what we get. Let's do that. So that's a 3 by 4 matrix. We'll just put all of the entries in, and then reduce row echelon form. And this is what we get. So what does that mean? Remember that this now corresponds to C1, C2, C3, because those are our entries of our unknown vector x. And so this says that C1 is 0, C2 is 0, C3 is 0. What does that mean? That means that the original system of equations that we started with had only zeros as the solution, which was in fact our definition of linearly independent. Okay. Now, when we start with zeros, a column of zeros, and put a column of zeros over here, that column of zeros is never going to change. So the only question for us, how can I end up, what would it mean to be linearly dependent? Well, it would be linearly dependent if I had values here or here or here. If I ended up getting a value for C1 or C2 other than 0. And the only way that that's going to happen is if we have a free variable. So let's look at that. So for this particular question that we saw, our answer was the vectors, the initial vectors, the set of vectors was linearly independent because we had no free variables. There were no free variables in that matrix, reduced row echelon form of that matrix. We had a pivot in every column except for the constant columns, which couldn't have a pivot. So we have as many pivots as we possibly could. So let's look at another quick example and then summarize. So what happens for that initial one that we started with? How about the vector 1, 2, it's just a simple 2 vector, 2, 4, linearly independent. Right, so we're going to exactly do exactly the same thing. We don't need to put in all of that extra work though. There's a bunch of middle stuff that isn't really necessary as far as answering this. What we really needed to do was make the matrix and add a column of zeros. Because this was like ax equals b, solve for x, the constant c1 and c2. So this is c1, this is c2. If we row reduce this matrix, what we're going to get is 1, 2, 0, 0, 0, 0. This is the reduced row echelon form of this matrix. We see here that C2 is free because there's no pivot in the C2 column. What this means is that C1 is negative 2 C2. So if we bring the C2 over to the right, C1 plus 2 C2 is 0. So C1 is negative 2 C2. C2 is free, which means that I have a non-zero solution to C1 times this vector plus C2 times this vector equals 0. Because if I choose anything for C2, I can figure out a value for C1 that makes this work. So we can find a particular one. If C2 is 1, then C1 is negative 2. If C2 is 1, then C1 is negative 2. And then I can say that negative 2 times this vector plus 1 times the second vector equals 0, which is certainly true. Because I get a negative 2 and a 2, a negative 4 and a 4. I could have chosen anything else for C1 or for C2 because C2 is free. Calculated C1, put those two values there, and we still would have gotten a solution set of easy equal to 0. So our summary, we're linearly dependent and independent. Set of vectors v1, v2, vn are linearly independent if the matrix that I get by putting those into columns, so we'll write that as the following, and then with a column of zeros, so put v1 through vn in a matrix, and then a column of zeros. And if that has no free variables, and so in other words, if there's a pivot in every of the first n column, so if it has n pivots, and they are linearly dependent in the other situation. If we have less than n pivots. All right, one last piece of this section. For that, we need a definition that's very related to what we just talked about. We say that a linear combination of vectors v1 through vn is a vector of the form C1 v1 plus C2 v2 plus Cn vn. So a linear combination of vectors is just those vectors added up with any different scalings. If I scale each vector by anything I want and then add them all up, what I get in the end is called a linear combination of the initial set of vectors. So example, if u is the vector 1 minus 2 and v is the vector 3, 2, then I can, if I take any scale of this, let's look at 2 times minus 2 minus 3 times 3, 2, and I can make that 2 and that 3 anything I want. They're not special here. But this is a linear combination of those two vectors. So I took those two vectors, I scaled them by whatever I wanted, and then I added them up. And in the end I get 2 minus 9, which is minus 7. I get negative 4 minus 6, which is negative 10. So this, negative 7, negative 10, is a linear combination of the original vectors u and v. that relates to span as follows. The span of a set of vectors, v1 and vn, is the set of all linear combinations of the vectors. Okay, so we'll do a few examples with this. Okay, so we're going to let W be the span of this. So again, we're thinking about this as a scaled version of the first vector plus a scaled version of the second vector. You want to think about these two things as dials that you can spin independently that change how much we're going to scale this and change how much we're going to scale this, and in the end we're going to add them together. So this is, W is the set of all of these things. Those are the linear combinations of the two vectors. We can ask a couple of questions. Here's another vector. Is this vector in W? So is this vector in the span of these two? In other words, is it a linear combination of the initial vectors? So what am I really asking? What that means is I'm saying, can we find a C1 and a C2 which solves this? And we've already seen questions that look like that. That's really very similar to what we just looked at a minute ago when we talked about linearly dependent and independent. The only difference was that we had a zero vector over here. But we still do exactly the same thing. How do I solve a question like this? This becomes the matrix 1, 2, minus 1, 0, 2, 3, 2, 1, 2, which then we need to row reduce and ask, does it have a solution? Solve for C1, C2. So let's row reduce. If we row reduce this matrix, this is what we get. Some things get a little tricky here, but remember that this really started, there were two variables here, C1, C2, and the constants, which means if we return this to a system of equations, it becomes C1 is 0, that's the top, C2 is 0, and the third line reads 0 equals 1. But 0 equals 1 means that there are no solutions. We have an inconsistent system. If it was an inconsistent system, then there is no C1 and C2 that work, which means that there's no way of scaling the first vector and the second vector to make the third, which means that I can conclude that 2, 1, 2 is not in the span of 1, 2, minus 1, 0, 2. Let's just look at one last example where it is consistent, where the answer to the question is yes, so that we can see how that will work. So is this vector in the span of these two? So we do exactly the same thing. We start with these two vectors as a columns of a matrix. We add 2, 1, the b vector, so this is like a, x equals b. We need to find the c1 and the c2, the scaling factors that might possibly, what could I scale this by and this by, so that when I scale and add, I get to the vector b. So we put our matrix in and we row reduce. And this is what we get. This corresponds to a consistent system because it reads C1 is 1, C2 is minus 2. And the last line is 0 equals 0, which is okay. That's not a problem. And so the answer to this question is yes, B is in the span of these vectors because the system that we get back is a consistent system. And so we can answer yes. And notice that notice we can even be more explicit here. Right? We can be very explicit. We can write down and say, since C1 is 1 and C2 is negative 2, I can say that 2 times 1 times 2, 3 minus 1, that's our C1, plus negative 2 times 0, 1, 2. See what I get? I get 2 minus 0, which is 2. I get 3 minus 2, which is 1. And I get negative 1 plus negative 4, which is negative 5. So there's our C1, there's our C2. The scaling factors that correspond to vectors V1 and V2. Put it all together and we end up getting B back. So B is in fact a linear combination of the first vectors, so it's in their span. That's what we need to say as far as the basics for section 1.3. At this point you should be in a good position to look over the homework and the quiz from that chapter. Once you're done with those, again, for sections 1.1 through 1.3, once you finish the homework and the online quizzes for that, send me an email, let me know that you finished that, and I will make the written quiz available to you. See you next time.